Welcome back. We're going to continue our review of Unit 4, Part 2. I'm going to start with the formulas that you're going to want to keep nearby throughout our lesson today. And I really suggest that you pause the video, you either write these down or even better yet, download the Unit 4 cheat sheet. These are all included there. So notice we have the net change theorem. I just want to point out that in the net change theorem, we always want to make sure we're taking the integral of the rate. And then that equals to just the original function without the rate on the right side. We need to be able to go forwards and backwards with that, so study that. And then from there, we actually have our first formula, and we'll see this later, which is the integral of velocity, which, by the way, is the rate of position, equals the change in position. And notice I say this works because v of t is just s prime of t, and if I have the integral of the rate, then on the right side, as we know, the rate and the integral cancel, and we're left with s of t minus s of 1, or the antiderivative of v. So this is actually our displacement formula. Here's another variation on that. You can have f prime of b minus f prime of a, but that will equal the rate of the f prime function, leaving you with the double derivative inside the integral. So see how that follows the same pattern? So this should be very, very familiar to you. The integral of the rate is the net change. We also from that have the net change corollary, which literally all we do is we just take f of a and we add it onto the other side in front of the integral. So we end up with this formula here. F of b equals f of a plus the net change. So study and know that as well. F of b will be what you're looking for. F of a is what's given, and you're just going to add on to that the change, which will be the integral of the rate of that function. Moving on, here's a variation on that. If I want the position at some time, I can take the earlier time and then add the change in position between the two times. Similarly, I can do that with velocity. So v of t2 time 2 equals the velocity at the first time plus the change in velocity. And this works because a of t is just v prime of t. Just three more really important definitions, which are total distance traveled. When we want total distance traveled, that's when we will use the absolute value, because we don't want negative distances and positive distances to cancel each other out. We want to know the whole distance, no matter which way we're traveling. So when we're dealing with the absolute value of v of t, make sure that you find the roots by setting v of t equal to 0 and then break up the integral at those spots. So I've highlighted my roots as x. If you're doing a Riemann sum problem and you have negative heights, just ignore the negative, make all heights positive. That will do the same thing as taking the absolute value. Displacement means the change in position. Again, displacement means the change in position. So over here on the left, I have literally the change or the difference in the position between B and A. And then this is how we represent it as an integral function, as the integral of the rate of position, or integral of v of t. This is the formula that I showed you earlier, and I said we'd come back to it, and here it is. So know that displacement is the change in position. But if I say I want the distance traveled, then you need to take the absolute value of v. So just one extra step. Finally, if I ask you for the average value of a function, of any function, that's the same thing as taking that function and dividing by b minus a. For example, if I say find the average acceleration, then you're taking the integral of acceleration. And this guy, kind of read it as the average. So we have average acceleration. Now, you may be inclined then, depending on the problem, to rewrite acceleration as v prime of t, and then from there use your net change definition to say, okay, that's just v of b minus v of a. But don't forget to multiply that by 1 over b minus a when you rewrite it, if you choose to rewrite it. But know all of those definitions. It's located in your cheat sheet. Okay, well, that's enough talking. Let's start doing. Number 25 says the function below shows the velocity of an object. So this is the graph v of t, measured in meters per minute from 0 to 18. Initially, the object's position is at negative 20. So initially means that the time is 0. And if the position is negative 20, they're saying s of 0 equals negative 20. And using units, that's going to be in meters. Position is always measured in meters. Velocity is measured in will be meters per minute. And then our acceleration will be meters per minute squared if we get there. So before we get anywhere, let's drop all of our perpendiculars. We're going to be using these areas, so let's find them all now. And then don't forget to drop the perpendicular from the endpoints as well. Triangle is 1/2 base times height. That's base 2. Height is 20, which is 40 divided by 2 will give me 20. This is a rectangle, so base looks like it's 5 from 2 to 7 times 20, so that's 100. This is identical to the other side. Okay, now that we've got all our areas labeled, we can go back to the problem. The displacement. So first I want to write down the definition. Displacement, and I'm going to use my cheat sheet, is the change in position. Oh, I knew that. The change in position. So I have two definitions that I can use, and it's your job to pick the right one. So either you can write s of 12 minus s of 2, or you can use the definition on the right side, which is the integral from 2 to 12 of v of t dt. So the question is, which definition of displacement will we use? Well, look at what you're given. For this definition, you need the position function. They didn't give us the position function. They gave us the velocity function. So we are not going to use this. We're instead going to use this definition because, again, it matches what they gave us. And this simply means find the area under the curve of v from 2 to 12. So let's highlight that. So since we're going in the regular direction from left to right, anything above the axis will be positive. Anything below the axis will be negative. So we'll have positive 100 plus 20 minus 5. And then we don't want this whole rectangle. We only want half of it. So that's going to be an area of minus 20. These 20s will cancel. 100 minus 5 is 95. We need our units. Well, if we want the antiderivative, the integral of velocity, that means that we're going to be not in velocity, but its antiderivative takes us to position. This is 95 meters, which makes sense if you know that displacement is the change in position. Okay, so I wanted to show you what I mean by you have multiple formulas. Choose the correct one based on what you're given. If they had given me this instead, position is given by the function 3t squared, then I would have definitely used this definition because I would just have to plug in 12, plug in 2, and then subtract them to find the change in position. But alas, we were given the v function, so we used the v definition. Letter B, it says calculate the distance traveled by the object from 4 to 10. So distance traveled is the same as total distance, right? Anytime we're talking about distance, we know our formula is integral from a to b of the absolute value of v of t dt. So we want the area under the velocity curve, but we want anything that's negative to turn positive. So let me make a note. Keep all areas positive. So we're going from 4 to 10. Let me adjust my limits. 4 to 10. Let me highlight that. And remember, we're finding distance, so everything will be positive. So this area here would be 60. positive, plus the 20, and then even though that's normally negative 5, we're going to make it positive 5 because of our absolute value. We want the total distance. So our final answer is 85 meters. That's the total distance that was traveled. Great. Part C says find the average velocity. Well, we'll set up a left-hand side. Average value of velocity is just going to be 1 over b minus a, so 17 minus 3, integral from a to b, from 3 to 17. Notice that order is so important. And since we want the average of velocity, then velocity is what goes here. So it's average velocity. Well, let's simplify the outside. That's 1 over 14. And now we want the area under the curve of v. Pause the video and go ahead and find it yourself. So again, we're moving in the regular direction from left to right. So positive 100 plus 20 minus 5 minus 40 minus 5. These are all going to be negative areas because they're below the axis. Then we're going to add 5. We're going to add 10. Now, since we're doing an FRQ, you could leave your answer like this. Anything that's equivalent to the final correct answer will be accepted. So on your notes, on your homework today, you'll see problems that say write an expression only. And that is just me telling you to stop right here. Okay, but we do still need units. Okay, that's a point on the AP exam. So just for fun, let's do this. So we have 85 over 14. Now remember, that was the average of velocity. Well, velocity is measured in meters per minute in this problem. So then the average velocity will be 85 over 14 meters per minute. Okay, D says calculate and interpret the integral from 3 to 11 of a of t dt. This literally just means the area under the curve of a. That's not what they want me to say. What we want is something that makes sense for a normal lay person. So we will use net change by crossing out a of t and writing instead v prime of t. Why? Well, this now allows us to use the property that says the integral of the rate is just the original function evaluated at the upper and lower limit and subtracting them. Oh, we can actually solve this now. We can find v of 11 because this is the v graph. Well, v of 11, well, here's 11. It'll be negative 10 minus, and then v of 3 is 20. The answer is negative 30. Negative 30 what? Well, this is the change in velocity. The change, because of the minus sign, in what? In velocity. Don't get distracted by the a over there. Whatever you're subtracting, it's the change in that. Look up here. We call this the change in position, right? That's our displacement, the change in position. So whatever is on the opposite sides of the minus sign, that's what the change is between. Since this is a change in velocity, our measurement should be in velocity, so therefore we are meters per minute. Great, let's continue. Letter E, find the average rate of change of position. Ooh, notice how the wording here differs. Find the average velocity. This one says now, find the average rate of change. So this is an MSEC problem. Average rate of change of position, so we're dealing with S. So it'll be S of, let's see, this is my A, this is my B, S of 6 minus S of 2 all over 6 minus 2. But they didn't give me an S function to plug into. So since there's no S of t, I know I have to rewrite this cleverly using net change. And here's how we'll do it. S of 6 minus S of 2 equals the integral from 2 to 6 of S prime of t dt. See how I used net change there? So once I have that, just don't forget to include 1 over 6 minus 2 in front, which is being multiplied. And notice what we've actually found here. S prime of t is really just v of t. And 1 over 6 minus 2 is in front, from 2 to 6, of v of t dt. Oh my gosh, we found the average velocity. So the average rate of change of position is really average velocity. That's so cool. Which makes sense, because isn't the rate of change of position velocity? Well, now that we've rewritten it like this, and remember, we had to do that because we didn't have an S function. Now we can actually solve this, just simply finding the area under the curve of V from 2 to 6. Okay, here's 2, here's 6. Width of 1, 2, 3, 4 times 20, that's 80. So this is 80. And we are multiplying by 1/4, so our answer is 20. Now, they ask for the average rate of change of position. So we're not dealing with S of t, we're dealing with its rate of change. We're really using the units of V of t here. So our answer will be 20 meters per minute. I hope that this is getting somewhat easier. I know my work is really messy, so I'm going to redo it. Bear with me for just 1 second. So let's do F. It says calculate the area under the curve of V of t, and then interpret it. Well, calculating it is as easy as just looking up there and adding our areas. So from 1 to 8, it looks like we have to find the areas of these trapezoids. If I just find one of the areas, this is symmetrical, so I can double it. The area of the trapezoid will be the first height, which is 20, plus the second height, which is 10. Okay, finding their average, times the width from 7 to 8, that's just 1. So that's going to be 15 for the trapezoid. So that's 15 plus, that's the first trapezoid, the 100 in the middle, plus the second 15 gives us 130. Okay, so that's the answer, but what's the interpretation? Well, the integral of V of t is the same thing as, rewrite this. Pause the video, see if you can actually finish this problem yourself. How should we rewrite V of t so that we can use net change and interpret it? So if you had rewritten it as S prime of t, you're correct, because we need the integral of a rate. Once we have that, we can write this as S of 8 minus S of 1, which is clearly saying the change in position. From time 1 to time equals 8, not the other way around. So since there's a change in position, our units will just be meters. Great. Next, G says find the change in position from 5 to 14. Well, change in position means S of 14 minus S of 5, which is another way of saying the displacement. Again, we don't have an S function to plug into, so we have to use net change, which says take the second term, that's your lower limit, upper limit is 14, and then S prime of t dt. Again, our graph is dealing with V, so we'll just rewrite that as V of t dt, and we're simply finding the area from 5 to 14. So we're going forwards again, regular positives and negatives. So from 5 to 7, that's 2 times 20, so that's 40 for this region. Plus 20, then we'll minus 5, minus 40, and we're done. 40 plus 20, minus 5, minus 40. Change in position means we'll be in meters. Okay, the next question, H, says find the position at time 18. So they want S of 18. As we said before, we do not have the S function. We have to use net change. In this case, we're going to use the corollary. And let's see if you can set it up yourself. So here's what the corollary says. what the question is asking for on the left, find another value that's given, and then add on to it the change in between those two values. Or more specific to our question, the position at time 2 equals the position at time 1 plus the change in position, which is the integral of velocity. So let's go ahead and apply that. Pause the video here and try it. By the way, you have to use this piece of information, which is the given position. So S of 18 equals S of 0 plus the change from 0 to 18. So you can always see the integral of the rate, and then we can make that change. Great, well, this S of 0 is given in the beginning to be negative 20. Now we just have to add on to that this piece, the area under the curve of V, the graph above, from 0 to 18. Oh my gosh, that's the entire thing. So from here, we would have got 140 minus 50, just doing it quickly, plus 25. Now, did you get 115? I think so. If I made a mistake, I'm sorry. I'm just going to write down 115. But don't forget, we had that negative 20 from our starting position, so that leaves us as our final position at t equals 18 at 95 meters. All right, part I says find a of 8, v of 8, s of 8. So a of 8, well, we don't have an a function, so we have to rewrite that as v prime of 8, which means we're finding the slope of the v curve at t equals 8. Let's go to t equals 8. All right, there it is. The slope, let's count. The slope of this piece is down 20 and over 2. So the rise is negative 20, the run is 2, so it'll be a slope of negative 10. And acceleration is in meters per minute squared. Now we'll find v of 8, which is simply the value at 8. So v of 8 will be that value right there, which is 10. And velocity is measured in meters per minute. So the velocity at time 8 is 10 meters per minute. Last, let's find s of 8. So we don't have an s of 8 or an s of t function, so we'll instead use our corollary. And since they gave us s of 0, we'll start with that. S of 0 plus the change from 0 to 8 of s prime of t dt, which is really v of t dt. Next step, plugging in s of 0 is negative 20 plus the change, or the area under the curve of v, which from 0 to 8, from 7 to 8, we calculated that trapezoid to be 15. So it's going to be 20 plus 100 plus 15. These 20s will cancel, and our final answer is 115. Since we're talking about the position at time 8, our final answer will just be in meters. So observe, we have meters, meters per minute, and then meters per minute squared. Cool. So this is like a true FRQ. You can actually get like 9 points on the AP exam just for knowing these definitions, and there's really nothing complicated about it, just being comfortable with these three, and then the definition of net change.